My name is Stella Van Ness, and this is my oral final exam for the Fundamentals of Astrophysics 1 class. The topics that will be discussed in this presentation are Compton scattering and inverse Compton scattering, as well as energy transport mechanisms in stars. In the first half of this presentation, we will focus on Thomson scattering, Compton scattering, and inverse Compton scattering, as well as what part inverse Compton scattering plays in high-energy radiation sources. Thomson scattering takes place when the photon energy is much less than the rest mass energy of a given electron. This results in an elastic collision, meaning that the photon energy does not change. We can find the cross-section of this collision by integrating over the solid angle d omega. The Thomson cross-section can be calculated to be 0.665 times 10 to the negative 24th centimeters squared. This diagram on the right shows the incident photon that is then scattered by the target electron. Compton scattering takes place when the energy of the photon is much greater than the rest mass energy of the electron. Unlike Thomson scattering, this is an inelastic collision, so the scattered photon and incident photon do not have the same energies. In the given equation, epsilon prime is the scattered photon energy. This equation can then be used to calculate the Compton wavelength. In the diagram on the right, we can see the incident photon hitting the target electron and then both the scattered photon and scattered electron moving away at a given angle theta. If an electron has sufficiently more kinetic energy than the photon, inverse Compton scattering takes place. The photon takes some of the electron's energy, resulting in a higher energy photon. The power radiated by the photon is proportional to the radiation energy. In the diagram, we can see a low energy photon hitting a high energy relativistic electron, thus resulting in a high energy photon. In high energy sources, photons are produced by synchrotron radiation. These photons are then scattered by the inverse Compton process and given a new higher energy, as we saw on the previous slide. We can relate the power of the photons produced by the synchrotron radiation and the inverse Compton photons using the magnetic and radiation energies of the source. This graph shows the flux versus the frequency of both the synchrotron photons and the inverse Compton photons, and we can see how closely the two are related. To conclude this half of the presentation, Thomson scattering takes place for low energy photons and non-relativistic electrons. This results in an elastic collision. Compton scattering takes place for high energy photons and relativistic electrons. This has an inelastic collision. If we have an electron that has a sufficient amount of kinetic energy, inverse Compton scattering allows for the incident photon to obtain a higher energy after it collides with the given electron. High energy photons can be created by a combination of synchrotron radiation and inverse Compton scattering. For the second half of this presentation, we will discuss the three types of energy transport in stars and when each type dominates. The three types of energy transfer are radiative transport, convection, and conduction. Radiative transfer is the most common form of energy transport in stars. In the diagram, we can see that photons can carry out energy from the core of the star. If the slope of the radiative transport equation is shallow, then radiative transport remains dominant. We can also refer to the radiative transport equation as the temperature gradient. If the temperature gradient becomes steep, then convection takes over. Convection involves the bulk motion of hot fluids. If the density of a bubble is less than the density of the environment, the bubble can expand and rise. Eventually, the bubble will contract and sink back down. There is stability against convection if the adiabatic temperature gradient is less than the temperature gradient. If this is true, then radiative transport takes over once again. We can also calculate the convection flux using the density and heat capacity due to pressure. The least common form of energy transport is conduction. This occurs when kinetic energy is transferred due to collisions of atoms or molecules. This is typical in high-density sources such as stellar cores and white dwarfs. We can calculate the conduction flux using the speed of the particles as well as the collision mean free path, which is represented by lambda in this equation. To conclude, if we have a shallow temperature gradient and the temperature gradient is less than the adiabatic temperature gradient, energy is transported via radiative transfer. This is the most common form. If we have a steep temperature gradient and the right density conditions, convection becomes the dominant form of energy transportation. In high density sources, like white dwarfs, conduction becomes the dominant form of energy transport in the star. Thank you.